Good, how are you?
Good. So what are we going to work on today?
Um, right now we are working on one sec, zeros of polynomial functions
Okay.
and the fundamental theorem of algebra and linear factorization theorem.
Okay. Do you have some problems we can go over?
Uh, yeah. There's one that says find the zeros of 3x cubed minus 20x squared plus 23x plus 10.
Okay. When you are factoring third or fourth degree polynomials, it is extremely difficult. It is
Mm-hmm.
not like we have a quadratic formula to plug it into. In
Yeah.
other words, as long as you're dealing with quadratics, every quadratic you can find the zeros by plugging it into the quadratic formula.
Mm-hmm.
But the moment you get to cubics and above, you can't do that. There are some techniques that occasionally work, like grouping, but this does not work for this particular function. Grouping doesn't work. So the only way we have of finding a zero now, are you supposed to be able to use your calculator or not?
Yeah.
To do this?
Well, we can. So it says the steps are to you have to put the factors of
All right, let's do it
10.
by hand because it sounds like they want you to do this by hand.
Yeah.
In other words, this wouldn't be that tough if I can put it into Wolfram Alpha and immediately it'll tell me the zeros.
Mhm.
Okay? So let's talk about the rational factor theorem. The rational factor theorem says that if there is a rational zero, that its numerator, p, will be a factor of the constant, and its denominator will be a factor of the leading coefficient
Mhm.
of the highest term. So P has to be a factor of 10 and Q has to be a factor of 3. So let's list our possible P's.
There's 10.
Plus or minus 10, plus or minus 1.
Plus or
On
minus
these, it's
5.
always plus or minus because minus 10 times minus 1 is 10. So,
Mhm.
and then what else we got?
Plus or minus 5. Plus or minus 2.
Okay, and what are our possible Q's?
Plus or minus 3 and plus or minus 1.
So our possible rational zeros are any combination of this. So let's list them. What are our possible P over Q?
10 over 1. Yeah.
What else?
Plus or minus 1 over 3. Plus or minus 1 over 1. And plus or minus 5 over 3. Plus or minus 5. And plus or minus 2 over 3, or plus or minus 2.
Now you can begin to see why this is such a difficult thing.
Mm-hmm.
Because we basically have 1, 2, 3, 4, 5, 6, 7, 8, 16 possible zeros.
Mm-hmm.
And the only way to figure out which one is to start going through and doing synthetic division.
Well, he said that we can kind of cheat by using our calculator to find which zero works.
Using your calculator's graphing feature or using your calculator to synthetically divide?
The graphing feature.
Okay, well let's do that. Let me pull it up on my Wolfram Alpha here. You know how to do this in your calculator? You know how to graph it?
Yeah.
Okay.
Yeah.
As long as you know how to do it. I don't feel bad using this. If you're not familiar with Wolfram Alpha, it's pretty darn useful. 3x raised to the third minus 20x raised to the second plus 23x plus 10. Have I ever done this? Have I used this with you before?
No, not yet.
One of the beauties is, unlike your calculator, it'll give you feedback as to what you put in. Sometimes, as you probably have discovered, that your calculator, if you don't get the right parentheses or something, what you put in isn't what you think you put in.
Yeah.
So that's the beauty of Wolfram Alpha. It immediately lists the polynomial. And it graphs it, and it gives you the zeros. The real roots are minus 1/3, 2, and 5. Notice that all of those were in our list. Minus 1/3, 2, and 5. So this had 3 rational roots. All of them were in this list. So we could have manually tried each one of these, and we would have discovered, since we know the zeros, let's just go through the process one time of proving that this is a zero, because this is worth knowing. Let's test 2. Okay?
Great.
How are we going to test 2? We're going to synthetically divide it. So here's what I'm going to do. I put the solution inside the little box. I put the coefficients of the polynomial, and you need to allow for every degree of x. So if there was one missing, you'd have to put a 0 in there. But this is for that one, that's for that one, that's for that one, and that's for that one. Okay. Now, the beauty of synthetic division is if this is a solution, if it's a 0, we will get a 0 as a remainder right there. If we do not get a 0, this is not a solution. So let's just test it to see. Do you know how to do synthetic division?
Yeah, you drop the 3, then multiply 2 by 3, and add it there.
Bingo.
Mm-hmm.
So that means it is a solution. And if we did that exact process with every one of our possible numbers, we would have gotten plus 2 would have worked, minus 1/3 would have worked, and plus 5 would have worked. Okay? So solving these, as you can see, this could be like a 20-minute problem if you had to do it without a calculator.
Yeah.
Now, the beauty of it is that when I synthetically divided it by one of the zeros, the answer is my remaining quadratic. So I can now say that one of the solutions is x minus 2, and you notice that we take the solution and subtract it from x. That's one of the linear factors.
Yeah.
The other linear factor, not linear factor, quadratic factor, is this remaining polynomial.
Yeah.
And clearly that must factor quite easily since we know what our solutions are. I'm going to take a wild guess and assume that that's 3x times x, and this must be minus 5, and this must be plus 1. So my three linear factors are x minus my solution, basically. In other words, this gives me the minus 1/3 solution, this gives me the 5 solution, this gives me the 2 solution. So if we are factoring this polynomial completely down to its three linear factors, this is what we would get. Once you find one of them, as long as you're dealing with a cubic, once you find one solution, getting the other two is pretty easy. Because when once you reduce it to a quadratic, it's easy finding the two zeros of a quadratic. Although not many people would tell you that, people who struggle with the quadratic formula, but it's actually quite an easy way to find the zeros compared to the harder ways of cubics, and it just gets harder as you go up. Quartics are even harder. Fifth degree polynomials become just terrifically hard to factor. One thing that's worth mentioning here, because it is a cubic, we know that there is one rational factor. There has to be, because you can only have three kinds of factors. You can have rational factors, you can have irrational factors, and you can have imaginary factors. Well, imaginaries always come in pairs, 1 minus 2i, 1 plus 2i.
Yeah.
Irrational factors always come in pairs. 1 plus or minus root 2. That's an irrational factor. Rational factors are the only ones that come along alone. So if we know that there's precisely three solutions because it's a cubic, quartics have 4 solutions, cubics have 3, quadratics have 2. So this being a cubic, it has to have at least one rational solution. Might have 2 irrational, or it might have 2 imaginary, or it might have 3 rational. But there's no way that it can't have a rational. So this little process works great on cubics. When you have quartics, there isn't necessarily one rational solution. You could have 2 complex and 2 irrational. So the rational factor theorem, you could spend a half an hour on a quartic searching out all 16 possible factors, and none of them might be correct. So this difficulty of finding the zeros of polynomials is truly difficult.
Yeah.
All right, you got another one you want to look at?
Yeah, I have a quartic.
Okay. This is going to be easier, and I'll tell you why, because you're going to tell me one of the solutions, aren't you?
Yeah. It's find all the zeros of x to the 4th minus 4x cubed plus 12x squared plus 4x minus 13. And given 2 plus 3i is a 0.
All right. So they gave you 1 0. They actually gave us 2 zeros. What's another 0?
2 minus 3i.
So if we were to divide this 4th degree polynomial by that 0, we would reduce it to a cubic. And then divide it by that 0, we would reduce it to a quadratic. So that's our goal. And to divide it, we're going to use synthetic division with imaginary numbers. Now, And we're going to do it twice. And when we get done, we better not have any i's left. Because by the time we divide this fourth degree polynomial by both of these imaginary solutions, we should be looking at a quadratic. A polynomial that's a quadratic that may have two more imaginary solutions, it may have two regular solutions. We'll find out. But let's do this. So tell me how to do this. That's the first step.
Then you put 2 plus 3i under the 4. Then it'll be negative 2 plus 3i.
Okay, we got minus 4. Oh, excuse me, my mistake. We're adding. Okay.
And it's negative 4 plus 9i squared, which is negative 4 minus 9. Right.
Let me look at this for a second. The i's cancel, yes. So it's negative 4 plus 9i squared, so that's 13, right? Hold it. Did I do that right? Plus, not, so yeah, negative 4 minus 9. That's minus 13. Okay?
Then it's minus 1. Then negative 2 minus 3i.
Okay.
We have 2 minus 3i. Then it's 4 minus, or plus 9, so 13.
What happened? We must have done something wrong here. In other words, we need to get 0. Or do we? Ah, see that negative 13? That was a negative 13. So we did get 0. Okay. Now, you do not want to stop here and list one factor as 2 plus 3i and the other factor as this cubic right here. Notice that that cubic has imaginary coefficients. We don't want to write cubics with imaginary coefficients. So we immediately do the second step, which is divide by 2 minus 3i. Okay. So we got 0 in both cases, so that proves that both of them were zeros, and we are left with a quadratic. What is this quadratic? It is x squared minus 1. So here are our factors. We have x minus 2 plus 3i. That's one factor. We have x minus 2 minus 3i. That's another factor. And then this x squared minus 1 becomes x plus 1 times x minus 1. Yeah. So those are your 4 solutions. Excuse me just one moment. Okay, Griffin?
Mm-hmm.
Okay. So did you get how we got to our final step there?
Yeah.
This resultant quadratic factored into x plus 1 times x minus 1. So our other two solutions are minus 1 and plus 1.
Okay.
And notice that if you stop at the end of the first division and you end up with this cubic with imaginary coefficients, that becomes problematic. I don't even know how to deal with a cubic with imaginary coefficients. But always know that when you do the second division, you're going to eliminate all the imaginary numbers and you're going to end up with a quadratic.
Mm-hmm.
Excuse me. All right. What else you got?
I have some more with imaginary numbers.
Okay.
So this problem says, write the quotient in standard form, and it has 3i over 4 minus 5i. 4 minus 5i and all that is squared. Or the bottom part is squared. Yeah.
Okay. Imaginary numbers are a little bit like irrational numbers. You don't ever want one in the denominator.
Okay.
Let's go back a step and let's see what we would do. Well, first of all, let's take away that squared for a moment. Okay? This is not a division problem. It is a problem where you have to make the denominator real in the same way that if I gave you 1 over root 3, and I would say simplify that, you're never going to give that as an answer because it has an irrational number in the denominator. So we would rationalize it by multiplying it by root 3 over root 3. We can always multiply a fraction by the number 1 without changing it, and that becomes root 3 over 3. So we have rationalized the denominator. So I say that when we have a problem like this, we need to realify the denominator. By that, we're going to multiply this thing by the conjugate over itself.
Mm-hmm.
And whenever you multiply an imaginary number by the conjugate, you immediately realify it. In other words, 4 minus 5i times 4 plus 5i is going to give you 4 minus 25, a negative 25, so it'll become 29. So the bottom becomes 29. We've made it real. Now the top still has imaginary numbers in it, but that's fine. That becomes 12i plus 15i squared, which is minus 15. So that would be the answer if that were the problem.
Mm-hmm.
Okay. They've made it 1 degree more complicated by squaring it. Well, what do I have to do here?
Well, you have to get rid of the squared.
Let's expand it. In other words, let's FOIL the bottom.
Mm-hmm.
What do we get?
16 minus 40i plus 25i squared. So
Which
minus
is minus 25. So in other words, we really have 3i over minus 9 minus 40i. Right?
Mm-hmm. Yeah.
Now it becomes much the same as the problem we just did, only a different conjugate. So we still have to multiply this by the conjugate. What's the conjugate going to be?
Negative 9 plus 40i.
And you have to multiply top and bottom by that. because you can only multiply a fraction by the number 1. And then the conjugate's guaranteed to turn the bottom into a real number. Let's see, what do we have? We have 81 minus 40i squared. So we have 81 plus 40, 121 in the denominator. In the numerator, we have minus 27i plus 120i squared, which is minus 120. So there's our answer. Now, do they want these answers in A plus BI format?
Yes.
Okay, so here's what our answer was. And to get it into A plus BI format, we're going to separate this into 2 fractions. There's the real part, there's the imaginary part. So it becomes minus 120 over 121 minus 27 over 121i. And there's your perfect form for the answer.
What I'm confused on is with that 4 minus 5a squared up top, how come you don't FOIL the negative 9 plus 40i times negative 9, or can you scroll up real quick?
Might have erased it. After I expanded this, I got minus 9 minus 40i.
Yeah, so how come you don't expand that, the minus 9 minus 40i times minus 9 plus 40i, the way you expanded the...
I did. I may just not have been totally clear about it. Let's make sure we do that. So I was multiplying.
Oh, because it's... Oh, so it's difference of squares, so it just...
Yeah, exactly. It was the difference of squares. In other words, it's nice to be able to recognize the difference of squares in factored form and in unfactored form. And anytime I got minus 9 minus something and minus 9 plus something, that's the difference of squares factored. So I know the answer is going to be 81 minus, whoops, I need to multiply that by 40 times 40. So that's 1600 I squared. So the answer I gave you was wrong. It's not this. I forgot to multiply the 40 times 40. So the denominator is going to become 81 plus 1600. So this denominator was 1681. So now when I split it up into 2 fractions, I'm going to have that is the real part and that is the imaginary part.
Okay.
Okay? And we were only doing half an hour today, right?
Yeah.
Okay. Good, because I got somebody else that's here waiting to do a session, so I was hoping that was the case.
All right.
All right? Okay, Griffin. Have a good week, and I'll talk to you next time.
All right, you too.